This is the beginning of section 10.2. This is day 1. And it begins on page 690. And we're going to talk about combinations. So what we talked about yesterday was a way of counting different arrangements, different orders, which we called what? Permutations. So what we're going to do today is we're going to talk about the difference between permutations versus combinations. These are both groupings and ways of counting different groupings. The difference between permutations and combinations is very simple. It all comes down to whether or not order matters. So if we take the same grouping and we just rearrange it into a different order, should it count as a different outcome? Should it count as a different result? Okay, and let me give you an example of what we mean by that. So let's say that we hold an election. Okay? And in this election, we're going to elect 3 officers. We're going to elect a president, vice president, and let's say a treasurer. Okay? So we can have all kinds of different outcomes. So let's say that we have Chris is elected as president and Nick is elected as vice president, and we'll put Naritsu as treasurer. These 2 are getting their 15 minutes of fame, right? All over the internet. All right. The question is this, guys. If I take those same 3 people and I arrange them into a different order, so let's say what we're going to do is we're going to have everybody vote for one person. And whoever gets the top number of votes is president. Whoever gets the second most votes is vice president. Whoever gets the third most votes is treasurer. Okay, that's how we're going to determine it. Each of these are different offices. They have different responsibilities. They have different jobs. So the question is, if instead of Chris and Nick and Naritsu, in this order, what happens if Nick had the most votes, and then Naritsu, and then Chris? Should that count as a different election result? Absolutely, right? Because now Nick is doing a different job. Naritsu is doing a different job. Chris is doing a different job. Does everybody agree this is a different outcome for our election? That's what we mean by order matters. If I take the same group of people or whatever it is that I'm counting and I just mix up the arrangement, it counts as a different outcome, a different result. So what is combinations about then? So what happens if instead of 3 officers, we're going to elect 3 representatives? To go to the school senate meeting. Now each class only sends 1, but let's say each class sends 3. So what we're going to do is we're going to hold another election. Everybody's going to vote 1 time for 1 person, and whoever the top 3 vote getters are, those are going to be our 3 representatives that go to the meeting. Are they doing different jobs? No. Is there any benefit of being the top vote getter versus the 3rd place vote getter? No. So the question now is, if it's Chris, Nick, and then Naritsu in that order, or it's Nick, Naritsu, and then Chris in this order, should this now be a different outcome for this situation? No, it's the same three people going to the same meeting. They all do the same job. There is no difference between first, second, and third place here. Now, there's a difference between first, second, and third versus everybody else, but there's no difference just by rearranging them because it doesn't make for a different outcome, a different result. Does everybody understand the difference between order mattering and order not mattering? Okay, so that's the idea. So let me give you guys, let me go over the formulas again, and then I'll give you some examples of situations that pop up quite often where order does not matter. For permutations, what was the symbol abbreviation for that? NPR, right? So n things chosen are at a time, but order matters. With combinations, it's the same symbol except it's NCR. Again, n things chosen are at a time, but now order does not matter. Okay? The formula for NPR was n factorial divided by n minus r factorial. For combinations, do you think combinations give us a bigger answer or a smaller answer? Why smaller? Order doesn't matter, right? So in permutations, right, if we hold the election for president, vice president, and treasurer, right, Chris, Nick, Naritsu, and Naritsu, Nick, Chris, and Naritsu, Chris, Nick, those are all counting as separate outcomes. But in combinations, when order doesn't matter, when we're just selecting three representatives, how many outcomes do all those different reorderings count as? Excuse me, one. So instead of, excuse me, instead of 6 outcomes, we would only get 1 outcome, because just rearranging is not enough to give us a new outcome. So what that means is we have to make it smaller, we divide by an extra term. And so it's the same formula, n factorial over n minus r factorial, but then it's going to be multiplied by another r factorial on the bottom. And that division by that additional number, that r factorial, is what's going to shrink our answer down. So for example, if I had president, vice president, treasurer, and let's say we know the top 3 vote getters are Nick, Naritsu, and Chris. Okay? We could either have Chris, and then Nick, and then Naritsu. We could have Chris, Naritsu, Nick. We could have Nick, Naritsu, Chris. We could have Nick, Chris, Naritsu. We could have Naritsu, Nick, Chris. We could have Naritsu, Chris, Nick. How many different outcomes did just those 3 people give us? 6, right? How do you come up with that? Using the formula. Well, that's going to be 3 people, and we're going to choose all 3 of them, but order matters. Right? So we're going to choose all 3 people for our election, but we're going to arrange them in different orders, which all count. That's going to be 3 factorial divided by 3 minus 3 factorial. That's 3 factorial over 0 factorial. 3 factorial is 3 times 2 times 1. 0 factorial is just 1. And so this gives us an answer of 6. There they are. 1, 2, 3, 4, 5, 6. You guys see how that formula gives us our result? But if I look at this group of people over here, so this ends up being 6 outcomes. So this is 3p3, and this ends up being 6 outcomes. But if I now grab these people, or these different results, and move them over here, how many outcomes should that count as? 1. Because order doesn't matter. It's still the same group of 3 people going to the meeting for us. So how does that work with this formula? Well, that would be 3c3, which would be 3 factorial over n minus r factorial times r factorial. That's 3 factorial over 0 factorial times 3 factorial. 3 factorial is 6. 0 factorial is 1. 3 factorial is 6. And what's 6 divided by 6? 1. So do you see how mathematically it gives us that one result? That extra r factorial on the bottom gets rid of all that duplication where all we did was flip-flop people around. That's the idea. And this is something that we saw similarly when we were rearranging the words on last night's assignment, right? So if you had 2 letters that were being repeated, you put a 2 factorial. If you had 3 of the same letter, you put a 3 factorial, because there were 6 different ways of rearranging those 3 letters, just swapping them for each other. All right, any questions about how the formula works? Now, are you really going to be using the formula most of the time? No. What you're going to do most of the time is you're going to be using your calculator, and just like you guys have NPR on your calculator, you also have NCR on your calculator. And so if we want to do 3P3, it gives us our 6. If we want to do 3C3, it gives us our 1. So what we need to do now is we need to talk about some of the applications of this. And one of the most common applications of this has to do with playing cards. How many of you guys have spent quite a bit of time playing with a deck of cards in your life and are familiar with the different kinds of cards and suits and things like that? Okay, not very many of you guys. So what I need you guys to do is I need you guys to look at page 690. On page 690, there's a little chart there. And that little chart shows you what a standard 52-card deck looks like. All the different cards of all the different suits. And so you have ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, and king of each of 4 different suits. You have clubs, you have spades, you have hearts, and you have diamonds, for a total of 52 cards in a standard deck. Okay? My recommendation to you, if you are not very familiar with a standard 52 card deck of cards, you guys need to Xerox off, or you can do a Google search or something and look for something along those lines also, or you can go to the online book and print that. Okay? That little chart there, guys, I will allow you to use on the test if you need it. You can't have anything written on it, but you can have that little chart that shows you what a deck of cards looks like. Okay? So I would make it now so that you have it to use on your homework, to use on your studying. You can use it on your quiz. You can use it on your test. Everybody clear on that? So that way, those of you that have not grown up playing cards are not at a disadvantage. Okay? You have it in front of you. So we're talking about a standard 52-card deck. So there are 13 different card values in each of 4 suits. So we have clubs, hearts, diamonds, spades. And we have 13 different cards. We have aces, 2s, 3s, 4s, 5s, 6s, 7s, 8s, 9s, 10s, jacks, queens, kings. How many of you guys have played poker before? Okay. So, how is it that I have more people that have played poker than people who know the 52 cards in the deck? I want to play poker with you guys. Because if you're playing poker and you don't even know what cards are in a deck, you're looking to lose a lot of money. All right. So, what we're going to do is typically we're going to be playing essentially what would be 5-card stud. How many of you guys have ever played 5-card stud? Okay, in 5-card stud, you're dealt 5 cards face down. You don't get to exchange any of your cards. You don't get to draw. You're just stuck with those 5 cards, and you make your best hand out of those 5 cards. Okay? So we're going to be dealt 5 cards. And what we're going to be interested in is how many different hands are there that we can be dealt. We're also going to be interested in things like how many different ways can we be dealt 5 cards so that we get 4 aces and then some other card as our 5th card. Okay, things of that nature. Or maybe 3 queens and 2 jacks. How many different ways could we get a hand with 3 queens and 2 jacks? Things of that nature. So we're going to take a look at how to count these things. Okay, and again, what we're learning right now is we're learning how to count. But again, we have to learn how to count systematically, because if we just try and figure out all of the outcomes, we're inevitably going to miss some. Remember the whole license plate thing, guys, right? How many millions of license plates did we come up with? It was like 17.5 million license plates just with that one configuration. There is no way in the world that you would ever just start writing down possible license plates and come up with the exact number of correct possible license plates. There's no way. You would miss some. You'd probably miss a whole lot of them. Right? Everybody agree with that? Okay? So we need a systematic way to count it. The same thing with these simple problems like card hands. So the first thing we want to talk about is how many possible hands there are. So here's where we have to ask ourselves a question. When we're counting poker hands, does the order that the cards are dealt to us matter? No, it does not matter to us. For those of you that have never played poker, whatever your cards are in your hand, the order that they're given to you doesn't make any difference. Okay? Especially in a hand like this where they're all dealt face down. It makes absolutely no difference. Now, there are certain poker games where the order does make a difference because some cards are dealt face down and others are dealt face up. You guys ever played baseball before in poker? Baseball is a game where it's a 7-card stud game. You get 2 cards down, and then you get 4 cards up, and then you get 1 card down. But if you get a 4 face up, that's like getting a walk in baseball, and you get a free card. You get an 8th card. But if that 4 is face down, you don't get an extra card. So there it would matter. But for a 5-card stud hand, it makes no difference the order. If you watch poker players play poker, what do they do with their hand? They're constantly rearranging the order of their cards. Okay? That doesn't change the value of their hand. So order does not matter. So since order does not matter, are we going to use permutations or combinations? Combinations. So order does not matter. So that means we're going to use NCR. So the question is this. If we want to know how many possible 5-card hands are there, how many different cards could we be dealt? 52. There are 52 possible cards that we could be dealt. We're going to use combinations. The question is, of those 52 cards, how many are we going to choose at a time to be dealt? 5. We're going to be dealt 5 out of 52 cards. And so that is 52C5, or 52 choose 5. Everybody understand how we set that up? The total possible number of cards is on the left, and the number that we're actually going to get is on the right. If we punch this into our calculator, 52 NCR 5, you will see that in 5-card stud, there are 2,598,960 different hands. Was it 598,960? Is that right? Yeah. There are over 2.5 million different possible starting hands that you can get with 5 cards. That's a lot, right? Okay. Any questions about that? Okay. Now, for those of you that play, just as a side note, how many of you guys play Texas Hold'em? Okay. So in Texas Hold'em, out of 52 cards, how many cards are you dealt? 2. You get 2 cards in Texas Hold'em. That would be 52 choose 2. There's 1,326 different 2-card hands you can start with in Texas Hold'em. Again, order doesn't matter, so that's why we use combinations, not permutations. Okay? This is a number where if you guys play poker for real money, you want to know things like how many different possible starting hands are there. Of those possible starting hands, how many of them are pocket aces? How many of them are pocket kings out of that 1,326? These are things that affect the probability and the odds that you need to think about when you guys are playing that game. Now, it doesn't make all your decisions for you, but it's one factor in your decisions. Okay? There is a lot of math involved. That doesn't mean that if you know math, you're automatically a good poker player. There's a lot more to it than that. But it is a very, very big component of being a good poker player. You have to understand the odds. No. We're saying that it doesn't matter if you get dealt a 2 of spades and then a 5 of diamonds, or if you get dealt the 5 of diamonds first and then the 2 of spades. Right? The order that you're actually handed the individual cards doesn't matter. You're just going to look at all 5 of them together anyway. Yeah, so we don't want to count, a 2 and then a 5, and then a 5 and then a 2 as different hands unless they happen to be different suits. And then those are different cards. That would count as a different hand. Does that make sense? Good question. Okay, everybody clear on this idea? So now let's look at some more interesting examples. So for example, what happens if we want to know how many different 5-card hands have all 5 cards of the same color? Now that's not a flush. We're not saying they're the same suit. They're just the same color. So you've got to really stop and think about this, guys. How many different colors are there? 2. And we want to choose how many of them? How many colors do we want to choose? 1. We want all 1 color. So the first decision we have to make is we need to figure out how to count the number of, we have to make a decision on what color we're going to get. So there are 2 different colors to choose from. What are the 2 colors? Black and red. Clubs and spades are black. Hearts and diamonds are red. And we're going to choose one of those. So that's where we chose the color. But in addition to choosing the color, we also have to choose the 5 cards. So do you guys see how this is 2 separate decisions that need to be counted individually? This is like choosing a bread and choosing a meat and choosing mustard or mayo, right? You guys see it's 2 separate decisions. First thing we have to do is choose a color. Then we have to choose what 5 cards we're going to get from that color. So given that we've now chosen a color, how many cards are in the deck that belong to that color? 26, half of the deck. So it's not going to be 52 choose 5. It's going to be 26. And we're going to choose 5 of those 26 cards. So first we narrow down 1 out of 2 colors. And then we narrow down the 5 out of the 26 either red or black cards that we need to count. Does that make sense to everybody? Now think about the bread and cheese or the bread and meat and condiment thing. What do you do with the numbers you get from those 2 decisions? You multiply them. Same thing here. So what we're going to do to figure out how many 5-card hands have all 5 cards of the same color, we're going to do 2 choose 1. 2 NCR 1. We're going to do 26 choose 5 and we're going to do what with those two answers? Multiply them. So 65,780 times 2. That means there are 131,560. 131,560. Different 5-card hands that we can be dealt that are all the same color. Half of them are all red, half of them are all black. So do you see how there were two decisions? That's a very important concept, guys, because another situation that we're going to get is we're going to get 5 cards, and we want 3 of them, exactly 3 of them, to be queens. So if 3 of them are queens, what are the other 2? Anything but queens, right? Something other than queens. So do you guys see that there are really 2 decisions we have to make? We have to make a decision as to what 3 queens we get, because there's how many different queens in the deck? 4. We want 3 of them. There's different ways that can happen, right? So we have to make a decision on what 3 queens we get, and then we have to make a decision on what 2 other cards we get. So we have a decision for the queens, and we have a decision for the other cards. And what are we going to do with those 2 answers? Multiply. So how many queens are there in a deck for us to choose from? 4. Again, order won't matter. How many of those 4 queens do we want to get dealt? So that's going to be 4, choose 3. Now, be careful. Here's where people mess these easy problems up. For the other cards, how many other cards are there for us to choose from? 48. Why 48? Because there are 4 queens, and our other 2 cards cannot include that 4th queen that we didn't get at the beginning. Does that make sense? So that's why it's 48 and not 49. Because it said exactly 3 queens, which means we can't accidentally get the 4th queen in the other 2 cards. We're not allowed to do that for this particular problem. Does that make sense to everyone? The other mistake people make is they put 52 there again, but you're not taking that from the 52. The other cards only amount to 48 cards, right? Because we have a queen of diamonds, queen of hearts, queen of clubs, queen of spades that are now gone from that choice. So it's 48, and of those 48, how many are we going to choose? 2. That's the other mistake people make, is they put a 48 and then a choose 5 there. We're not choosing 5 other cards, we're only choosing 2 other cards because we want 5 cards total. 3 of them are queens, that's this number here. 2 of them are other cards. So now we're going to punch this into our calculator, and you can do it all at once if you like. 4 choose 3 times 48 choose 2. There's 4,512. Different hands that involve 3 queens and 2 other cards. It's a lot of different hands, right? So does everybody see how we put these things together? So your first job when you read these questions is you have to decide how many different actual decisions have to be made. And set up your lines for each decision, and then figure out how to count the choices for that particular decision. And then once you get those all filled in, then you multiply the answers together. You guys think you can do that? Okay. Now the other thing you're going to have to do is you're going to get problems, word problems, where they describe a situation. And you have to stop and really think about the situation, because they're not going to tell you whether it's permutations or combinations. So what are you going to have to decide by reading the question? Does order matter? If I have the same group in the outcome, but I get them in a different order, does that count as a different outcome? Okay, again, if you're playing Texas Hold'em and you get 2 cards and you get an ace of diamonds and then an ace of spades, is that a different starting hand than if you got the ace of spades first and then the ace of diamonds? No, you still have an ace of diamonds and an ace of spades, regardless of which order they were given to you in. Okay? So that's very important for you guys to decide whether a rearrangement matters. If you're betting on a horse race, okay, and you have the top 3 finishing horses, win, place, and show, does it matter the order that they come in? Yeah, right? First, second, and third place pay different amounts of money, right? So it absolutely matters. So that's going to be what? Permutations or combinations? Permutations. So you're going to use NPR. So you have to first decide whether it's NPR or NCR. Does order matter? Does order not matter? And then you have to decide how to count it up. Questions about that? Okay, that's it, guys. Let me give you the assignment.